Hi, everybody. My name is Lucas Amorim. I am a senior vulnerability researcher at Palo Alto Networks. Today, I'm going to be talking about finding vulnerabilities in Python applications, especially in more specifically in the native extensions using fuzzing. So what is fuzzing? So fuzzing is a technique used to find vulnerabilities and misbehavior in software. So the whole idea is provide invalid and unexpected input or random data to a given endpoint or a given function. And the second part is we have to have visibility to find out when things have gone wrong, like when a crash occurs, or when there is a potential memory leak or potential memory corruption. So so there are two main, not main, but the two most well-known fuzzing tools are AFL and libfuzzer. Those two are the ones I'm more familiar with, but today I'm gonna only be talking about libfuzzer because that's the one I have been using to fuzz Python native extensions, right? So in libfuzzer, to use libfuzzer, you need to have access to the source code. So we need to compile the source code with the fuzzing instrumentation using Clang, and you also need to write some code to trigger that to start the fuzzer, the fuzzer, right? So libfuzzer generates mutations. So basically, you give a seed, or it creates some random data, and trying to reach some areas of the code, and also keeps track of which areas of the code it has reached, and it tries to generate mutations in the data so it can reach deeper and deeper parts of the code. So this is an example. So as I mentioned, like you have to write some code. It's not a whole lot. So what you have to do is you need to have this function LLVM fuzzer test, one input, and then inside that function you called the function you want to fuzz, right? So this is specifically for C++ and C. We're gonna get to the Python later on in this talk. So, but here we are fuzzing this function, do something interesting with my API. So basically, the data is the random data that the fuzzer will generate, and this is the size of the data that is going to be generated, right? So you pass that down to your function, and then the libfuzzer will keep track of which areas of the code has been reached, and will try and mutate that data in each interaction. So it tries to reach deeper and deeper in your code. And it also provides you with code coverage, so you can get a report to see which areas of your code are being reached and which areas are not being reached, so you can modify your seed, which is your initial data, to get deeper into the code. Right, so for example, as I mentioned, that I had that example, I'm using Clang here, and I'm adding the fuzzing instrumentation and compiling that, and then I'm just running the binary here. So as you can see, it runs and it starts libfuzzer. We didn't provide a corpus, so we're starting from scratch. Right? It's starting empty, and we have a coverage of 1, and so yeah. So the whole idea of seeds is, so you don't want to, you want to make sure that you have a valid input to begin with. So let's say if your endpoint expects an image, a PNG image, it might take forever to the fuzzer to, if we start from scratch and let the fuzzer create the data from scratch without any initial data, it will take forever to actually get to a format that it's a valid PNG image, or at least it's closer to a valid PNG image. So the whole idea is you provide a bunch of seeds, which is our valid data, and you let the fuzzer to mutate that data, to modify that data, and get to, and try and trigger unexpected behavior. So another thing that helps with the fuzzing technique is the sanitizers, right? Especially the address sanitizer. So the whole idea is not every single bug or memory corruption will cause a crash in your application. So sometimes you might have a memory corruption and nothing's going to happen, just your application will misbehave, but there is no way for us on the outside to know that that occurred. For example, if you have in C, if you have a double free, which means the free function in libc was called twice for the same memory address, right? That might not trigger a crash, right? But when we have the sanitizers, let's say address sanitizer, it will trigger a crash because the address sanitizer modifies the malloc, and the free function and other stuff. So it makes sure that when there is a memory corruption, it triggers a crash. So it let the fuzzer finds out there was a crash and realize there is a problem, and then it stores that for you, right? Otherwise, you might not even know that there was a crash. There are several really good ones. The main one I use, as I mentioned, is the address sanitizer, because this is the one more specifically for the kind of vulnerabilities that I'm going after, which is memory corruption vulnerabilities, buffer overflow, heap overflows, use after free, double free, and so on and so forth. Yeah, so here we have an example of one of Fuzzer running. This is actually a real one that I've been running against one of really well-known Python library. So some things that we need to point it out here is, as we can see, we have the coverage here, and this number has always been increasing, which means that your Fuzzer is able to generate enough data to reach deeper and deeper into your code, right? If this data is taking forever to increase, if this number is taking forever to increase, it means that the Fuzzer is having a hard time to generate enough data to reach other parts of your code. And the second line, in the end here, we have the strategy that's being used to generate that, to mutate the data, right? So shuffle bytes, change bytes, which means that the Fuzzer it's getting the data you have, it has mutating that data, and it's changing it in unexpected ways. So one thing I would like to point out is efficient Fuzzer, right? So you got to make sure that your fuzzing is really efficient, because I have had cases where I had a Fuzzer running for days, if not weeks, and it turns out it wasn't doing much. So the reason was I just basically compiled the application with the Fuzzer, with the fuzzing instrumentation, and I run it, and I was like, okay, that should be it. And it didn't catch anything good for me, right? You will find cases where you just need to compile application with the fuzzers, the fuzz instrumentation, and run it, and you catch bugs right away. But that's usually application that hasn't been fuzzered yet, so you're basically cutting just a low-hanging fruits, right? When you have more secure targets that have been hit by researchers heavily, you need to make sure that your fuzzer is efficient. One strategy I use to validate my fuzzer is I try and find a vulnerability that was fixed in that given software, and then I roll back to before the fix, and I try to make my fuzzer to catch that bug. So if my fuzzer is able to actually reach that part of the code and catch that bug, so I know my fuzz it's working well. So what I do is then I go back to the latest version and start fuzzing the latest version. So Corpus, it's part of the efficient fuzzing. So basically, you want to make sure that you're keeping tracking of the output data you're generating, and Corpus is a good way of doing this. Because sometimes you're gonna reach a plateau, and you need to make sure that your inputs are good enough to get out of the plateau and keep going deeper into your code. So Corpus is a good way of doing that. And then you see when you run the fuzzer that it keeps creating corpus, right? If you've been running the same fuzzer for days, and you go and check, and the number of corpus being generated hasn't increased, it means there's something wrong with your initial data, with your seed data. So yeah, I have mentioned that before about like the seeds. It's the initial data you're gonna provide to your fuzzer. You don't always have to. You can let your fuzzer create the random data by itself, but it might take a while, especially when you have specific file formats. Then it might take quite a while for your fuzzer to be able to generate enough random data that will match that file format. And so that's why it's important to have a seed, especially a really good one with like several cases, valid cases, input data for your fuzzer. Another thing that's really important to mention is dictionaries. So Dictionaries has a name explained for itself. It's common words that's being used in your fuzzer. Let's say if you're fuzzing like XML or JSON, it's good to have a dictionary showing what is that it's expected by that endpoint, what is the file format, so the fuzzer can use that dictionary to generate data and then mutate that data to try and trigger vulnerabilities or misbehaving. All right, so we talked about C++ and C. I showed some examples. Now, how can we fuzz Python extension without writing any C or C++, right? So Google has released this project, which is basically a wrapper around libfuzzer. It's basically Python code that you can write, and you can fuzz your Python application. I have been using this project quite a lot. It's really good. There are a few things missing, but for now it has working great for me. So as I mentioned, it's based out of libfuzzer. So this is a quick example. I took that from the GitHub README of the repo. So we have the test one input, like similar to what we had in C++ and C, right? Which receives data because it's Python. We don't have to pass the size, and then in here we would call a function, and then the function will be fuzzed with the data, which is just this is bytes. And then here, setting up the fuzzer, and then starting the fuzzer. So as I mentioned, you need to compile your code with the fuzzing instrumentation, and the way I have done that, it's I just specify my compile, Clang or CLang, and with the instrumentation flags, and then I just use pipe install, and then when pipe, of course, this is a image processing library, so I clone it to my local file system, and then I just do a pipe install in there, and then it's going to use the CLang to compile it, and then I'm ready to fuzz it. Right. So this is actually a real example I have used. So that's using this is fuzzing pillow. Same as I showed before, we have test one input receives the data, and then here I'm using image.open, which is from pillow, and pass the data, the data, and then call loads. So when call load, you're trying to load up that imager, and it might trigger some vulnerabilities. It's important to mention that in here I'm only basically fuzzing whatever it's called by the .open and .load, right? So in some other cases, you want to fuzz different functions. If that's the case, then you have to call those functions right here. And yeah, and to run that, I need to make sure that I'm preloading the address sanitizer fuzzer. So the way I do this, I use Python to find the exact directory where this is located at, and then I called my code. Here you might notice that I'm using a few other flags like the LLVM profile file, and I use like dump coverage, which means that it's gonna try and create a report of that of the code, so the coverage. So what areas of the code is reaching. I have had some issues with Python specifically to generate the reports. I'm not sure if it is a bug or there is no support yet. I haven't had the time to actually investigate that further. And the last three parameters here is the output. So basically where it's going to store the output, and the seed with the directory with my initial set of inputs, and the corpus, which is the one that's going to be generated by mutating the seeds. Right. So here I screenshot of running me running that fuzzer. So as we can see here, every time that a new function is called, we have here new pine funcs, which function is being called. And these are just the pillow outputs. And then we can see it generate a bunch of data, and pillow is basically complaining that it cannot identify the image, right? And it keeps going down, and you see new, different functions being called, like underscore open, underscore token. That's when so the fuzzer is mutating the fuzzer, and it's reaching new areas of the code. And when a new function it's called, then we have here it shows us here that a new function was called. Right. And in here we can see there was a vulnerability that was triggered. So this vulnerability was basically so we have there was a malloc being called with super high numbers. So malloc could not allocate that amount of that size. So here's the size, and then it crashed, right? So as we can see here, it says the allocation size is too big. That's the kind of error that was generated. And the test case was written to crash dash this UID here. Right? I'm pretty sure this was actually also a bug in the libfuzzer, not a bug in the library itself. I don't quite remember, but I need to double check that. But as we can see here, it shows exactly where that happened, and then you can go and you can take a look, and then you can take this test case, and then you can run that individually, and then you can investigate further and find out whether this is actually a memory corruption or it's not or not. That might be really small for you to read. But yeah, so here again, this is me was fuzzing simple JSON, which is a JSON parser for Python with some C extension. And again, we can now see here the new functions being called. Basically, I'm only fuzzing the loads function in dash init. And then here we can see the coverage. We can see the output with the strategy being used by the libfuzzer and the coverage. Yeah, so after running that for a few hours, I got a few crashes. So we can see here in the directory where we had the crashes. So we have 4 crashes. We have the corpus directory, which is generating the mutated data. For this one specifically, I did not specify a seed, so it's starting creating basically random data from scratch and mutating that random data to a point where it started reaching new areas of the code. And once it started reaching new areas of the code, the fuzzers realized that, okay, so this data I'm generating is good. I'm able to go deeper. So it uses that to feed itself as a seed and keep it going deeper and deeper and deeper. Right? So as I mentioned that I fuzzed for a few hours, and without a seed, and it was able to generate like almost 5,000 different test cases those are test cases that made the code go deeper and get more coverage. Right, so we have some here. I'm taking a look at the crashes. So this is the data that was generated that created a crash. This has all been fixed already, so no problem here. Yeah, so fuzzing, it's really interesting. It's a good way to find vulnerabilities. Sometimes, especially when we have code that is really complicated to understand, or you don't have the time and it's too big. So fuzzing is a great way of finding vulnerabilities, and I'm just happy to see that more and more now has been adopted by the whole community of vulnerability researcher. And yeah, if you have any questions, please reach out. We can talk about after this talk, or you can send me an email or connect with me on Twitter or in any way you want to. Okay, thank you very much.